Okay guys, tonight's lecture is going to be all conceptual. We're going to first investigate acids and bases and see what their properties are like. By definition, acids produce hydrogen ions. We can also call a hydrogen ion a hydronium ion. Real quick, just to show you, when a hydrogen ion goes into solution and it reacts with water, it forms a hydronium ion. Now, the hydronium ion is not stable, so for the first time all year we see a reversible reaction. And that hydronium ion can break back down into water and hydrogen ion. This happens in equilibrium. That means that the rate at which the hydronium ions are breaking back down and the rate at which the water and the hydrogen ions are coming together is the same rate. So we don't really notice this happening. You can't see it in your glass of water, but it is happening. Okay, bases, on the other hand, they are compounds that produce hydroxide ions in aqueous solutions. Let's take a look at some properties that scientists have discovered about acids and bases over the years. You're going to have to copy this down under the tab of acids versus bases on your foldable. Go ahead and pause and write this stuff down real quick. All right, the physical state of acids tends to be a gas or a liquid, and bases come as solids. Acids, you know from if you've ever tasted a lemon, they taste sour or sharp, and bases feel slippery like soap. They both produce electrolytes in solution. Electrolytes are ions, and since acids produce the hydronium ion and bases produce the hydroxide ion, these are considered electrolytes. Acids tend to react with water as well as metals, which we've seen in the lab as we've mixed a magnesium ribbon with hydrochloric acid before, and we produced hydrogen oxide or hydrogen gas. Bases also tend to react with water. They also react with fats and oils, and this is how soaps used to be made before we had surfactant-based cleansers. Continuing on with our little table, there are two types of acids and bases that scientists have identified. In 1890, Svante Arrhenius was the first person to identify acids and bases officially. He told us that acids increase the hydronium ion concentration in water. And he also told us that bases increase the hydroxide ion concentration in water. This looks a lot like the definitions that I have typed up above, and in fact they're one and the same. The problem that Arrhenius had with these two basic definitions is that our amphoteric species could not be classified. So what is an amphoteric species? An amphoteric species is a chemical that can act as an acid and a base. Water is one of those types of chemicals. Water can act as an acid or a base. It depends on what it's reacting with. The second group of acids and bases that have been developed are what we call the Bronsted-Lowry acids and bases. Two gentlemen in different countries, Johannes Bronsted and Thomas Lowry, within just a few months of each other, published the exact same idea about an acid and a base. They both said that any chemical that donates a proton, which is a hydrogen ion, is considered an acid, and any chemical that accepts a proton is considered a base. And so the two go hand in hand. If you look closely at the two definitions for Arrhenius acids and bases and Bronsted-Lowry acids and bases, if a chemical qualifies as an acid under either definition, it qualifies as an acid for the other definition. So if we have a Bronsted-Lowry acid, we also have an areneous acid. And if we have a Bronsted-Lowry base, we also have an areneous base. All right, when we first learned about acid-base reactions, way back in chapter 7, we learned that they are double displacement reactions. Well, sometimes these types of reactions occur where water and a salt do not get produced. And when that occurs, we have something called a conjugate acid and base forming as two products. In this example here, make sure you write this down as well as the definitions. The hydrogen from the nitric acid gets donated to the water. So the hydrogen is acting as an acid because it's donating. Let's see here. And after it's donated the proton, and we can show that here, this proton, this hydrogen ion, gets donated to the water, okay? Once it's done that, now we just simply have a nitrate ion floating around in solution, and we end up with what we call a conjugate base. A conjugate base is a base that is formed after an acid has donated a proton. Conversely, when we take a look at the water, and here's the amphoteric part of water, after water is accepting, as water accepts the hydrogen ion, or the proton here, it acts as a base because it accepts a proton. But afterwards, on the product side, now it has become a conjugate acid. Remember in the last slide, I told you that the hydronium ion, H3O+, is not really very stable. So it wants to get rid of that hydrogen again. So when the conjugate acid decides to let go of this extra hydrogen and form water again, that extra hydrogen will go back and create the acid again. So this is what we call a reversible reaction. The reaction goes in both directions. Now, conjugate acids and bases, students don't tend to like, but they're really not as difficult as they may seem. If we take a look at hydrofluoric acid is an acid, and its conjugate base then is the fluoride ion. After the hydrofluoric acid has donated its proton, it now is left as just being a fluoride ion. So we have hydrofluoric acid as our acid, and the fluoride ion now becomes our conjugate base. Some acids are considered diprotic or polyprotic acids, and phosphoric acid is one of them. So we have H3PO4. We call it polyprotic. I'll write that down for you. Polyprotic. Let's break that down. Poly we know means many. Protic means proton. So phosphoric acid has the ability to release 3 protons, all 3 hydrogens. So when it acts as an acid, right, we know this is an acid from our rules that we've learned throughout the year. But once it first acts like an acid, then it becomes H2PO4-. So this is a conjugate base. However, it can continue to lose. If this continues to lose hydrogen ions, then it continues to act as an acid until there are no more left. Let's recap. Conjugate acids are acids that are formed after a base accepts a proton. So if we were to take a look here at this ion, if it acts as a base and becomes phosphoric acid again, it has accepted that proton again. Our last topic for today is our discussion about neutralization reactions. Acid-base reactions are also called neutralization reactions. The reason why is because the ending solution in your beaker or flask has a neutral pH. And we haven't really talked about pH yet. We'll do that in our next lecture, but I know we've all heard of it. So basically, the solution ends up being neutral. It's not an acid or a base anymore. It's neutral. Some things to keep in mind: water is neutral, and a neutral pH is 7. Again, we'll define what pH is officially in the next lecture. Neutralization reactions have their own laboratory method. We call it a titration. A titration is the lab method that's used to determine the concentration of an unknown substance by adding a solution that we know the concentration and volume of until the run is complete, until we have completely neutralized the unknown solution. The equivalence point is the point at which an acid-base reaction is complete. The moles of the acid equal the moles of base, therefore the pH is neutral. Now if we take a look at the picture here, this is what a setup looks like in the lab for a neutralization reaction. You have to use a ring stand. Instead of a ring clamp though, we use, instead of a ring, we use a clamp to hold this new piece of glassware right here called a burette. It's glass. It has a little handle on it. We call it the stopcock. And it turns so that you can add your liquid. It's graduated, and this is what you fill your standard solution with. That way you know how much you've added, and we also call that the titrant. The sample that we want to titrate goes in a flask with some indicator in it, and here we have that magenta pretty pink that we've worked with throughout the year, phenolphthalein. It's a pretty neat setup, and it's kind of fun to work with, but the method requires extreme precision. You cannot add 1 drop extra because then you will have gone beyond your equivalence point and you will not have the same number of moles of acid as you do base. Okay, so the last thing that we need to talk about is how we calculate the concentration of an unknown acid or base once we have run the titration. We use the formula MAVA equals MVBV. Yes, it looks just like the dilution equation. We're going to withhold any examples until we work with it in the classroom. This is it for tonight. I hope you guys have a great evening.